The question is, could you do an example on finding deformation of a statically indeterminate axially loaded 1D rod? Here's the problem that I have chosen here, which is patterned after a problem that I have discussed in some of the previous videos. We have a 1D rod with 3 segments, each with a different diameter, Young's modulus, and length. The values of the diameter are given on the picture. The values of the Young's modulus and length are given in this table. The rod is fixed at point A. At the right end, we have a fixed point in the vicinity of point D. The question is to find the displacements of the interior points B and D, first by assuming that points D and E coincide with each other. In other words, this fixed point is right at point D. So we have a fixed support at point D. And then by assuming there is a gap and the value of the gap is 0.3 millimeter. Let's start working on the first part where point D is fixed. While this is a simple problem, it's a good idea to get into the habit of verifying that this is indeed a statically indeterminate problem. We go ahead and mark the support reaction. There's one at point A, one at point D, and therefore number of unknowns is 2. Number of equilibrium equations we can write down for this problem is 1, and therefore Nu is greater than Ne, and therefore this problem is statically indeterminate. 2 unknowns, and therefore we need 2 equations. The first equation comes from the equilibrium. Here it is. The second equation is going to come from displacement compatibility. In this problem, our compatibility condition is going to be that the displacement at point D is 0. Let's go ahead and start working on that. First, we will calculate the deformation of each segment, AB, BC, and CD, and then sum them up in order to come up with an expression for the displacement of point D. We set that to 0. Before I go to the next slide, let me point out that you do have another method to solve this problem, which is to use the principle of superposition, which leads to what is called the force method. But here we will follow the displacement compatibility method. The first thing we want to do is to find the internal axial forces in each of the 3 segments. Obviously, we won't be able to find numerical values for them since we don't have the support reactions at this point. The best we can do is to express them as a function of the support reactions. So here are the details. We have done this a couple of times already, so I won't spend any time on the details here. Here are the expressions that I got. NAB is minus AX, NBC is minus AX minus 25, NCD is minus AX minus 13. You may want to note that I kept using the left side here so that these expressions will be just in terms of AX and not AX and DX. This simplifies matters a little bit going forward. Now let's go ahead and find expressions for the deformation of each segment. Note that I have listed the expressions we got for the axial forces in the same table that was given to us. Here are the details of the calculation of the deformation of segment AB. Deformation of segment AB, UAB, is given by this expression where NAB is the axial force, LAB is the length, EAB is the Young's modulus, little a, AB is the cross-sectional area. And from this table, NAB is minus AX, and let's say we express that in kilonewton. Length is 1 meter. Young's modulus is 200 gigapascal, so let's convert that into kilopascal or kilonewton per meter squared by multiplying 200 by 10 to the 6. Cross-sectional area is pi r squared. R is 5 millimeter, right? Diameter is 10 millimeters, and therefore radius is 5 millimeters. So express that in meters, that will be 0.005, right? So we get this for UAB, minus 63.7 times 10 to the minus 6 times AX. You can see from the units I have on the right side here, the unit of this deformation is going to be meter. Here are the other 2 sets of calculations, and I'm sure you can easily follow them. Now we can apply the displacement compatibility and generate our second equation that we need to solve this problem. The displacement compatibility here is that the displacement at point D is 0. We come up with an expression for the displacement at point D by summing up the deformations of each of the three segments. So here it is. So here are the details of the implementation of this compatibility equation. There are two common things in each of these expressions. The sign is negative, right, in each of these cases, and there's a factor of 10 to the minus 6 in each term, right? So I factored them out, and then inside the bracket we have 63.7 times AX from the first deformation, UAB, and then here we have 10.9 times AX plus 25, and here we have 62.9 times AX plus 13, right? Alright, so we simplify this, we get a value of minus 7.9 kilonewton for AX. Our question is to find the displacements of the interior points B and C, right? Those displacements are going to depend on the deformation, but the deformations are only a function of AX. It does not involve DX. Remember I mentioned that the way we did the internal forces is going to simplify matters a little bit, right? This is what I'm talking about. I don't even have to use the equilibrium equation in order to answer the question. But of course, if the question is to find the support reactions as well, then you don't have a choice but to go back to the equilibrium equation in the end in order to find a value for dx. Here's a summary of the results we got so far. Let's go ahead and calculate the displacements of the interior points B and C. Here are the details. The displacement of point C comes from the deformation of segment AB and segment BC. So you add the two and we get a value of 0.317 millimeters for that. And displacement of point B comes only from the deformation of segment AB. And that works out to be 0.503 millimeters. Now let's go ahead and work on part B, where we do have a gap between point D and point E, given by this value right here, 0.3 millimeters. The difference between what we need to do here and what we did before is in the displacement compatibility equation. Earlier, the displacement at point D is 0, but this time use of D must be equal to delta gap. Delta gap expressing in meters is 0.3 multiplied by 10 to the minus 3. As part of part A, we have done a lot of the preliminaries that we need in order to continue here. We already found expressions for the deformations of each of the segments in terms of AX. So I took the steps we used in part A and simply modified it. So on the right side, instead of having 0, now we have a number. And that leads to this value for AX. There is one thing you want to do before you proceed. How do we know that the displacement of point D is actually greater than delta gap? If it is less, point D is not even going to touch point E, the fixed point E, and therefore there cannot be any reaction between point D and point E. In other words, the reaction at point D has to be equal to 0, right? If the displacement of point D is greater than delta gap, then point D will try to go beyond point E, and then a compressive force will develop at this point. But if the displacement is actually small, in other words, displacement of point D is actually smaller than delta gap, but we try to enforce this type of displacement compatibility. What are we trying to do? We are pulling point D all the way to point E and attaching it at that point. So if that's what we are trying to do, there's going to be a tensile force at this point. So we can resolve this issue by calculating the reaction at point D and seeing whether it is a compressive force or a tensile force, right? So let's go ahead and do that using the equilibrium equation. So here are my calculations. I took the equilibrium equation, which is AX plus dx equals minus 13, and I substituted this value for AX and came up with this value for dx. dx is minus 2.9 kilonewton. Here's our free body diagram drawn for the beam, right? We marked the reaction at point D as a tensile force, right? but it turned out to be a negative number, and therefore this force is actually pushing on the rod at point D. In other words, it's a compressive force, and therefore our assumption that point D moves past point E is a correct one. So here are my calculations for the displacements of point C and point B. In comparison to what we did in the earlier case, all we have to do is to use this value for AX. So here are the values of the displacement I got for point C and point B.